Now that we have a thorough understanding of how thermocouples work and how thermocouple circuits react, let's go over a few quick notes about thermocouple construction and ratings. By international standards, all thermocouples are constructed using different pairs of alloys for the conductors and have been assigned one of 8 letters and color codes to determine the thermocouple type. The letter not only identifies the alloys, but also indicates the temperature range for the thermocouple. The 2 most common thermocouples used are J and K. Okay, let's practice using this chart. From the example we have been using, answer these questions. What type is the thermocouple? What does a brown jacket mean? What is constant tan? What is the maximum temperature you can use this for? Okay, let's take a look at the chart. From the example, we know the 2 conductors are iron and constant tan. So when we look at the chart, albeit a small one, we have that iron is the positive lead and constant tan is the negative lead, so that makes it a type J. It has a brown jacket, so what does that mean? Well, according to the chart, that means it's the thermocouple grade, not an extension wire. What is constant tan anyway? Well, apparently it's an alloy of copper and nickel. And what is the maximum temperature? Well, if we look at the maximum temperature range for a type J, we find that the highest temperature it can be measured and worked with is 2,193 degrees Fahrenheit. Notice on this table of thermocouple characteristics that both R and S types measure the same temperature. The difference is in their signature voltage over temperature response curve. Another factor that separates these types is their thermoelectric difference called the Seebeck coefficient. The voltage curves and Seebeck coefficients are beyond the scope of this course and are mentioned here to ensure that you do not replace one thermocouple type with a similar ranged one, like swapping an R for an S. Closeness doesn't count. It won't work. The construction of commercial thermocouples can be very simple, like the fused end style used in our lab experiments, to sealed units as shown. On sealed units, the actual junction is at the tip, and the internal wires are passed through a series of ceramic beads to the thermocouple cabling or board. Thermocouples can also be designed to fit inside a special housing called a thermal well, which assists maintenance when changing the thermocouple. Okay, we've covered a lot of ground, so let's take a moment and do some review. First of all, the hot junction. It's not necessarily hot. It's also known as the measuring junction, which is probably a better name for it. The cold junction is not necessarily cold. It's also known as the reference junction, which is a better name for it. The Seebeck effect only generates voltage when? Well, when there's a difference in temperature between 2 junctions and you're using dissimilar metals to create the effect. If the measuring junction is warmer than the reference, then the voltage is positive. So by extension, what does that mean if it's negative? Well, then that means that the reference junction is warmer than the measuring junction. Okay, now we're going to spend a bit of time practicing some of the stuff we've learned. Remember that the voltage read at the extension junction is the sum of the 2 other junctions. And you cannot directly measure the voltage of the measured junction at the reference junction because you are creating another thermocouple circuit. Okay, here's our first example. A thermocouple's measuring junction is placed in the process stream. The extension wires are extended to the voltmeter leads. This generates a measured voltage of 7.78 millivolts. Using the charts, what is the temperature? Well, before we go there, we have to ask ourselves a couple questions. First of all, what is a type of thermocouple? Well, since they're using iron and constantan, that would make it a J-type. Number two, is the J2 and J3 junctions at 32 degrees Fahrenheit or 0 Celsius? Well, they're in an ice bath, so yes. So now we can go to the chart. Okay, scouring the chart, we find 7.789, and if I look and find its location, is in the 6th column, and I shoot across to my left, and it's 140. So 140 plus 6 gives us a temperature of 146 degrees Celsius. Okay, here's one that's going to work the other way. We have a type J. What would the expected voltage be if it was 15 degrees Celsius? All right, so the first thing we do is we have to find 10 in the left-hand column. So we have our plus 10, and then we shoot across until we find the 5 column, and where they two meet, we find it reads 0.762 millivolts.